There's a beeping sound, but I don't know what that is.
Hello, everyone. Thank you so much for joining us today. This is Matthew. I'll be asking the questions, and I'm going to hand this over to Chris for a quick introduction, and then we will get started with questions from you.
Okay, welcome everyone to the open session for the online class. There's a lot of you online today. I think people seem to be finding a little more time to do things online now that they can't actually go to work. So it is a different world we live in. Everyone should stay safe, and whatever country you happen to be in, practice whatever safe measures your government and local leaders recommend, as we do here. So the floor is open for your questions.
All right, Chris, the first one is from Arnie Grugel, who's on with us live, who says, the way that we discover other exoplanets and exomoons is through their shadows, right? And so it's around a star. But that star is so far away that it might not exist anymore, yet we discover them and they're exoplanets. Is it correct to assume that these actions might be since these actions are in the past, that we're discovering new planets which are already gone and dead and no longer around?
That is indeed possible in principle. So the question is alluding to the fact that it takes light a significant amount of time to reach us from stars. And actually, for many of the exoplanets found by the transit or eclipse method using Kepler, those are actually quite distant stars. So Kepler was looking at a small patch of sky, and the brightness of the objects was typically 14, 15, 16th magnitude. And their distances were hundreds of light years, actually going up to a few thousand light years. So indeed, the light from those stars and the planets that pass in front of them is thousands or hundreds of years old as we receive it by our telescopes. The reason why this probably doesn't amount to something weird going on and observing things that no longer exist is that the time scale of evolution of planetary systems and their parent stars is so long compared to the light travel time from these regions of our galaxy that it doesn't really mean much. The main sequence lifetime of the sun is 10 billion years, and so a few hundred or a few thousand years relative to that lifetime is very small. Even more significantly, most of the stars that are being looked for exoplanets are stars like the sun. They're main sequence stars. And we can tell by the spectroscopy, the spectra of the stars, what evolutionary stage they're in. And when they're on the main sequence, you can tell when a star starts sputtering towards the end of its life and changing its fusion rate and varying in brightness and so on. So stars get unstable near the end of their lives, and we can see that pretty easily. So none of the stars we've looked for planets around or found planets around are actually near the ends of their lives. So therefore, they're unlikely to be in a category where we got that light, it's a few thousand years old, and in the intervening few thousand years, the star is gone.
Okay, thank you very much. The next question is from Sebastian A., who's on with us live, who asks, an extremely massive pulsar has recently been discovered. Is there any difference between a neutron star and a pulsar? How can we determine the mass of a pulsar?
It's hard to determine the mass of a pulsar. So the general statement is that pulsars are a subset of neutron stars. So when a massive star dies and it leaves behind a compact core, a collapsed core that's between about 1.5 and about 3.5 times the mass of the sun, that will formally fit the definition of a neutron star. So it will collapse to a state of pure nuclear matter where the protons and the electrons are fused together. The loss of electric charge in the remaining neutron material means there's no force to resist further compression except the fact that the nucleons are sitting right next to each other in the equivalent of a massive atomic nucleus. That's a neutron star. Neutron stars in principle are dark. They don't emit any radiation, and it would be impossible to see, but a small fraction of them have imperfections and blemishes, and actually because of matter that's drawn onto them by gravity, they emit a feeble amount of low energy radiation, radio waves, by the cyclotron emission mechanism. And that's what we see as a pulsar. And the pulsing of a pulsar usually reflects most of this radiation coming from a hot spot on the surface of the star. And generally, the radiation emerges from the magnetic pole regions of the pulsar and is polarized for that reason. So we look for polarized radio emission that pulses. So only a very small fraction of the likely large number of neutron stars in our galaxy, 30 or 40 million in total, have been observed. We have catalogs with maybe 4,000 or 5,000 pulsars. So that's what pulsars are relative to neutron stars. And I actually just forgot the beginning of the question, the first part of the question too. Matthew, you don't remember that?
I'm sorry. The first part of the question, was, is there any difference between a neutron star and a pulsar? And basically, there was recently a massive pulsar discovered.
Right. There's no fundamental difference. The mass of the other part of the question, of course, was how do you measure the mass of a pulsar? If you see that it is a neutron star and that is its evolutionary path, then you essentially know you've determined the range of mass. It must be larger than what would be a white dwarf, about 1.4 times the mass of the sun, and smaller than an object that would be formerly a black hole, about 3.5 times the mass of the sun. So you confine it to a pretty narrow range. Directly measuring the mass of neutron stars is very difficult. Essentially, they have to be in binary systems. That's really the only way we can measure the mass reliably of any star in astronomy.
Thank you, Chris. The next question is from Lalamelek from Turkey, who says, I've read many books about astronomy and quantum mechanics and have been struggling with reality since my enthusiasm for these topics because I'm starting to feel like nothing is real and time is an illusion. Do you feel this as an astrophysicist? And what do you think about time and wormhole theories and time travel?
Yeah, I would say it's a dangerous thing to read too much. We got an echo. We just suddenly acquired an echo, Matthew or Alexander. I'm not sure why. I'll keep going though. Yes, it's a tricky thing to read too much quantum theory because you can become untethered, unmoored. It is very strange. The rules that apply to the subatomic world are indeed very different from the macroscopic world. I think we can still maintain some tether in reality because even though the microscopic world is governed by probabilistic rules, that's what quantum theory really is. There are no certainties, only probabilities of where a particle is or what its energy is or its velocity or pretty much any property you can measure. Those probabilities are constrained by the theory of quantum mechanics. They can't take any value. And so it's not like all rules are off in the subatomic world. And so particles do have mean properties and they do have average expected positions and energies. And so it's not like a Wild West in that microscopic world. The question of reality, though, is a much deeper one. Quantum physicists would just say there is what we can measure. And there's a limit to the ability to measure things in the microscopic world. And so the Heisenberg uncertainty principle is really a limit in the precision with which you can measure something. It's not an uncertainty in a fundamental sense, it's more a limit of precision of measurement. And there is no way to circumvent that limit, so we believe it's a fundamental aspect of the physical world. That doesn't mean we throw reality out of the window. Now, the fact that a particle can seem to be at two places at once or various different places at once, or that a photon can be split in a physics experiment and travel down two paths and then recombine and show some influence between its states in the two different paths. These are strange phenomena of quantum theory. They do indeed beg some profound questions about reality. And physicists have essentially tabled this philosophical debate about reality just for the fact of understanding the theory, calculating, measuring, and saying that the theory does allow us to make measurements and observe the world in a coherent way. So they've sort of tabled this thing that for the average person is profound and quite disturbing. And I'm somewhere in the middle. I mean, I've read enough quantum theory to know how it works and to be disturbed by some of the aspects of Bell's theorem and the indeterminacy or the coherence of quantum states across significant distances, not just within an atom, but across meters or kilometers. It's been demonstrated This is very disconcerting. And I would just say we don't have a good philosophical backdrop for which to understand this physical theory. So work still needs to be done.
Thank you, Chris, for reassuring us. The next question is sort of a series of questions from several people who have questions related to the expanding universe. So Lawrence, Beth, and Ilsa, who are on with us live, kind of ask, if the universe is expanding and becoming less dense, how could we possibly crash into the Milky Way because of local motion, gravity? You know, if the universe is expanding so fast, how is that possible?
The collision is with Andromeda rather than, so it's our galaxy with Andromeda that's projected in 4 billion years. So the universe is expanding fast, but the distance, the speed of expansion between any 2 points in space-time is proportional to the distance between those 2 points. So if you're talking about modest distances in the universe, then the expansion rate is not that incredibly large. For example, the Hubble constant, the measure of the local expansion rate, is a number like that's close to 70 kilometers per second per megaparsec. And that means for every megaparsec, or 3.25 million light years away you go from the Earth, that's somewhere past Andromeda, the average expansion rate of any 2 points is 70 kilometers per second. That's a very high speed, but at 70 is a fraction of 300,000 kilometers per second. The speed of light is actually quite low. So on scales of typical scales between galaxies, the expansion rate is small compared to the speed of light, so it's not super fast. Now, why is Andromeda falling towards us? Why are we going to collide with that in 4 billion years if the universe is expanding? Well, it is always possible for individual galaxies, pairs of galaxies, groups, even clusters of galaxies to essentially exempt themselves from the expansion of space-time because their mutual gravity, if their mutual gravity is strong enough to overcome the expanding space-time that's pulling them apart, then they will indeed start to fall together. And then that's why we have galaxies that are bound to each other, binary galaxies, or clusters of galaxies that are circling around each other and not going anywhere in terms of an expanding universe. And that's why we can have Andromeda that's close enough to the Milky Way, and the masses of the two objects are large enough that that gravitational attraction overcomes what would otherwise be space-time expansion in this region of space. And so we will eventually fall into Andromeda in about 4 billion years.
Right, and then the next kind of related question is, in an expanding universe, there's more volume. Does this mean that there's also more matter or more energy?
That's an interesting question. I mean, you can sort of think of the universe as a container, and as the space-time expands, the contents of that container get diluted in just an obvious way. And that calculation works pretty well. It's not completely correct, as I'll get to in a minute. And so as the universe expands, the density of matter in any particular volume of space, particular absolute chunk of space, does go down. And as the universe expands, the density of radiation in the space goes down. There's actually an extra effect, because as space expands, the wavelength of radiation grows. That's the redshift. And so energy you lose the energy both by dilution of the increasing volume and by redshift. And that means that the sort of overall effect on cosmic dynamics of radiation is dropping off faster than the effect of matter and its gravity. And so the universe was once radiation dominated very early on, but as the universe has expanded, the radiation has lost its power essentially by this extra factor of the redshift, and so mass now dominates. Now the wild card in this is dark energy. So dark energy is the dominant component of the universe. And while normal matter and dark matter and radiation indeed dilute in any particular volume of space as time goes by, the same is not true of dark energy. Dark energy appears to be an intrinsic property of the vacuum itself. And if it has the form that was characterized by Einstein 100 years ago, even though he didn't understand the measurement of the expanding or accelerating universe, that wasn't in hand then, he conceptualized in a physics sense something that we might call dark energy. The dark energy retains its value, its magnitude or amplitude in any volume of space as the universe expands. And that, in essence, is why you have an accelerating expansion. So dark energy is exempt from this dilution effect.
Thank you, Chris. The next question is from somebody local, Tucson Blue Skies. Do you ever do any local talks, and are you involved with near-Earth asteroid verification or validation on Mount Lemmon?
I do give local talks. I gave one in our College of Science lecture series a couple of months ago with Batul Kachar, one of our young astrobiologists. We're talking about life beyond Earth and leaving the Earth and so on. So that was in Centennial Hall. And I give talks fairly frequently. Many of those talks that I had on my calendar for the next month or so have been canceled. I was going to talk at the book festival. That was canceled in Tucson, and other things are being canceled too. So that's unfortunate. I mean, I kind of like giving public talks, and people like to go to them, but that's not what we're doing right now. We're doing this on video. So there's a lot of stuff going on, and there are plenty of public talks that you can catch on the internet, and I guess that's the best way to do it in this mode, the safest way to catch a public talk now.
The next question is from a live viewer, Wolf and Bree. Have you ever filled in the Drake equation with your own variables? Is there a place to find that, or can you talk about what your thoughts are on the possibilities for your own interpretation of the variables?
Sure. I've probably written articles that speculate what those terms might be. It's a favored astronomer game because, you know, anyone can have their own opinion. So the classic formulation of the Drake equation, which, to give the overview, is a set of 7 numerical terms which combine to give the number of presently communicating intelligent civilizations in our galaxy, the Milky Way galaxy. The first 3 or 4 terms of that equation are now known. The rate of which stars form in our galaxy overall per year, number of new stars per year in sort of sun-like stars, the fraction of those sun-like stars that have planetary systems, the mean number of Earth-like planets per system, the probability that those planets are habitable. Those are all terms that have now been measured, and the last couple just in the last 4 or 5 years using Kepler data. And if you multiply those factors together, the first 4 factors of the Drake equation, you get a number that's not too far from 1. It may be, you know, a fraction like 1/10 or 2/10 or 1/2 or 1. So that's interesting. And then you have the final fractions, which are the probability that having a habitable Earth-like planet, life actually develops, then the probability that that life becomes intelligent, the probability that that life becomes has civilization or technology, and then the lifetime, L, of that civilization in the communicable state. So the next 3 factors that we don't know are fractions too. And the question is, how small are those fractions? We simply don't know. And so, you know, I have in the past said, well, maybe those fractions are 1/10, that if you have 10 potentially habitable planets, 1 in 10 gets life on it. Some people might say, well, all of them do, given enough time. So that might be 1, not 1/10. Anyway, it's impossible to know what these factors are. That's why we have to do the experiment. But in my own version of estimating them, or just guessing in some sense, I put the product of those factors at around 1 part in 1,000 or 1,000th. And then you have the final term, which is the lifetime of the civilization in the communicable state. And if that lifetime is, say, somewhat longer than us having technology, which is a couple hundred years, make it 1,000 years, then you take that 1,000th back up to 1. And you actually do potentially conclude that we're unique in the galaxy as a presently communicating civilization. But if I've been pessimistic in those last fractional numbers, the product could be 1,000 times higher. And then we have 1,000 pen pals in the galaxy. So you can see how hard it is to properly estimate the Drake equation when 3 of the factors are unknown and the lifetime of a communicable civilization is also unknown. So 4 unknowns. Obviously, you can get whatever answer you like.
Thank you very much, Chris. The next question is from Rishab, who's on with us live, who asks, with new quantum computers, will we be able to model do a 3D model of the entire universe?
Quantum computing is helping astrophysics, but not much yet. That's because quantum computers are still in their infancy. Quantum computing is essentially a way, rather than the standard computers that are built on simple switches, simple logic switches, which have a 1 or a 0. They have inputs and then they have an output, which can either be 1 or 0, and you just take a vast number of those switches to do your calculations. Quantum computers create, instead of a bit, which is 1 or 0, they create what's called a qubit, which is a probabilistic state rather than a 1 or a 0, on or off, light or dark. And what this essentially does is parallelizes a calculation. It enables you to do a tedious calculation in smaller chunks in parallel, and therefore increase the speed of the calculation enormously. That's the potential of quantum computers. But constructing a quantum computer, even if you know how to do it in principle, is quite hard, because these superconducting semiconductor technologies that let you build a quantum computer are extremely challenging. They're not the mature technology by which we can say take a silicon wafer about the size of a postage stamp and put 100 billion transistors on it, which is something we can do now. So quantum computers are in their infancy from a sort of manufacturing standpoint, not from a theoretical standpoint. And I would say we're still probably 10 or 15 years away from them being able to contribute meaningfully to calculations such as the 3D contents of the universe. But when they mature, they will, of course, do such calculations enormously quicker and cheaper than current computers. And so these calculations will advance very rapidly from that point.
Thank you very much, Chris. The next question is from Robert Brady, who's on with us live, who asks, are there telescopes that allow programming from home? And I thought maybe you could talk about professionally and then also for amateur astronomers.
Well, telescopes that allow you to program your observations from home, if that's what the question means, then yes, there are. There are observing networks or amateur astronomer networks and some crowdsourced networks, and NASA runs one called the Micro Observatory, where you can essentially put in for observations over the network and get an image delivered or get data delivered. So in that sense of programming from home, yes, there are some small telescopes. These are typically a few inch up to 6, maybe 8-inch telescopes with CCDs, so they can do reasonably deep observations. It's a growing trend in astronomy, and not just for amateurs or for recreational astronomers, but professional astronomers are using these methods too, because some of the most important science being done in astronomy involves monitoring objects that are intrinsically quite bright, so you don't need a big telescope, and just gathering data relentlessly on them for days, weeks, or months without stopping with every clear night and every clear hour. And that takes dedicated arrays of these telescopes. So professional astronomers are actually getting good use of this technology. But it's certainly available for the members of the public too, to take their own data, to participate in observing campaigns, and to do what we would call citizen science.
Thank you very much. The next question is from Alfonso, who would like to know, there's a question that's sometimes used in science fiction themes. If we discover intelligent life on some planet, but with a level of development that's inferior to our own, should we contact them or visit them? What are your thoughts?
It's an interesting trope of science fiction, I guess, that how do you handle first contact with alien civilization? It has been argued that when we travel, we will most likely encounter civilizations less advanced than we, because we're the ones doing the traveling. So we need spacecraft, we need efficient energy sources to go between the stars. If we are contacted by aliens, they're almost certain to be more advanced than us for the same reason or an analogous reason, because they've left their planet and come here. they are more facile with traveling between the stars than we are, because we can't do it at the moment. So if we go, we'll likely see more inferior or less well-developed intelligent species. And if they come, they'll be very advanced. And they may be so advanced as to find our technology uninteresting or our level of intelligence uninteresting. We may not even be worth talking to. That's a rather sobering thought, but I guess the Copernican principle would say that's the most likely outcome.
All right. The next question is from a live viewer, Rana. Is there a material that is sensitive to sound that we can use to find out more about cosmic sounds? And generally, people are interested in sounds from space or sounds made from data from space. So can you talk about how those are collected, how those are created?
So fundamentally, sound doesn't travel in space. Sound doesn't really mean anything, that concept, because space is an almost perfect vacuum. And sound is compression waves of air molecules caused by a disturbance. That's the sound that we're dealing with right now as you listen to me. In space, that kind of audio signal or sound cannot propagate because there are no molecules or particles to carry it. However, there is a very active field, subfield, if you like, of astronomy or outreach or communication that's called sonification. And it's the method, it's a very popular method, and it's quite appealing. It's a good way of experiencing parts of the cosmos in a new way. Sonification involves taking a signal that is not a sound signal fundamentally and converting it into sound just through some algorithm or some calculation. And clearly, you can do that. The classic example from the last few years is gravitational waves. So gravity waves are essentially the oscillations of space-time, and we've seen situations where black holes merge and the black holes coalesce, and there's this amazing oscillation that occurs in the space-time, and then this ringing, which is a sonic word, that gradually dies away. And so people have taken the space-time ripples and their frequency and just converted them to a frequency of sound waves, and that leads to these black hole chirp signals, which you can find on the internet if you just Google black hole merger or gravity wave chirp. You'll actually find sound files representing some of the black hole mergers that LIGO has detected. That's a classic way of doing sonification. Another way that's been done a number of times in the past is to use the oscillations of the sun. Sun has hundreds, literally hundreds, maybe thousands of modes of oscillation of its plasma. And you can turn those various modes of oscillation into a very rich sonic signal. There was actually a very well-known piece of music that was commissioned by the Kronos String Quartet 2 decades ago, and it's been played at NASA centers in various places around the country, including Tucson. That's the sonification of solar signals based on solar oscillations. So anything that oscillates or vibrates or does something other than make a sound wave can be converted into a sonic signal. And it's a very interesting way of experiencing something and thinking about a scientific phenomenon in a new way.
Thank you very much, Chris. The next question is from Richard, who is on with us live, who says that the James Webb telescope is delayed yet again. Do you know what's going on? Do you have any comments? What are your thoughts?
The James Webb Space Telescope's really in a tight spot because it's so over budget. It was, of course, originally had a budget under $1 billion, I think, right at the very beginning. It's hard to imagine because it's now well over $8 billion. Congress put a cap on the budget around $8 million and told NASA not to exceed it, but at some points in the last few years of testing, it's gone over the top because there's still things. There was a shake test, as many people know, about a year ago, that some pieces of the telescope assembly shook off. The instruments have been separately undergoing their tests, and the instruments look in pretty good shape. People are worried about the telescope structure because it has to assemble itself or unfold in space and array and fold out solar panels. A lot of moving parts of this telescope. which is scary, given that it's going to be at an unserviceable location. No astronaut could come and fix it. So for all these reasons, and to make it as likely to work as possible, people have sort of been throwing money at the James Webb Space Telescope. And the longer it takes, the more that marching army of engineers and scientists gets paid. And so its total budget at launch, if launch is as advertised in October 2021, will be about $10 billion. And there's a hint that it could slip further, as the question alluded to. NASA's being extremely guarded about launch delays beyond 2021 because it would be, for PR terms, very bad. Congress has expressed strong displeasure at the cost overrun of James Webb, and also astronomers have expressed displeasure because it's essentially stopping astronomers from doing the next big thing because James Webb is so expensive. It's in the too big to fail category, which is not a good place to be for an astronomy project. I of course do hope it works. I hope it goes on its current launch date. If it slips more than a month or so, it loses its place in the queue for a launch, and so we'll again have to wait a year or so. And it's so far behind schedule and so far over budget that it's almost hard to remember what it actually was originally supposed to cost or when it was originally supposed to go up, which is over a decade ago.
Next question is from Fredel, who says the Japanese recently landed a craft on an asteroid and will be sending some soil back to the Earth. Do you know what they're looking for, and what do you expect they will find? For example, water?
Yeah, Japanese have had some excellent technologies deployed on comets and asteroids. OSIRIS-REx is the local mission that's trying to do a similar thing with the asteroid Bennu, but actually the Japanese sort of have beaten OSIRIS-REx to the punch, and their sample will come back to the Earth first. The hope is that asteroids are primordial material for the formation of life. We know that some of the organic material that was on the early Earth when life started was delivered by extrasolar bodies like comets and asteroids. So sampling this sort of primordial solar system material dating back all the way to 4.5 billion years ago on a pristine asteroid that's never been touched, and bringing that sample back intact into the lab is an amazing achievement. And what they hope to find, of course, is organic material. I don't think they realistically expect to find living organisms or microbes. That's very unrealistic because the physical conditions are very harsh. They might see more complex molecules, hydrocarbons of some length, fatty materials, lipids, other things, the basis of nucleic acids. So there's a chance they could see some complex molecules beyond just the fact that they're carbon rich and organic. And that will be very exciting. And also, they're going to look for evidence of hydration, evidence that liquid water was once inside the body and may have even been liquid within it at some point early in its history. And at that point, if they can show that, there is a chance that there could have been microbial life inside. Any object that has liquid water and organic material and therefore a local source of energy because it's very far from the sun, so there must be heat to keep water liquid. That's a place where you could have microbial life.
The next question is from G-Funk, who's on with us live. Do you have any comments on the Milky Way and the newly revised estimate of its total size?
Yeah, the size and mass of the Milky Way are numbers that you think we would know by now because this is our galaxy, right? We've been studying it for a long time with big telescopes, and we're within it. But new data is coming to life all the time. The most impressive new data set is from the Gaia satellite from the European Space Agency. And this is a satellite that's doing astrometry. It's a kind of unglamorous part of astronomy where you measure the positions of hundreds of thousands, or in this case, millions, actually in the end, billions of stars, faint stars in the Milky Way. And from those measurement of positions over time, you can measure the proper motions, the space motions of these stars and their distances. So the Gaia satellite and other ground-based observing in the last few years has allowed us to map star motions in a big chunk of the Milky Way galaxy with more precision than ever before. And that, of course, has inevitably led to revisions on the size of the galaxy and the mass of the galaxy. And they've both gone in the upward direction. I can't say whether they've converged yet because Gaia is still gathering data. And these are not enormous corrections. The Milky Way is not like 2 times bigger or 2 times more massive than it used to be, but they're quite substantial. And this new data is making a big difference in what we understand about the Milky Way we live in.
Thank you, Chris. The next question is from Rebecca Charnow, who would like to know if black dwarfs fade away, and what do stars do that are small when they run out of fuel?
Right. So a star is by definition an object that has fusion, that has energy production inside by the fusion process. As you go down the mass spectrum of stars, when you get to something like 1/10 the mass of the sun, you get to a star that actually can't do what the sun is doing, which is fuse hydrogen into helium in a 3-step process. You have a star that can only do the very first step, which is go make deuterium from protons. That's called deuterium burning or deuterium fusion, and it's a very feeble energy source. So a star around the 1/10 the mass of the sun can do this. Below 7% of the mass of the sun, there's insufficient energy for fusion to occur at all. So the question alludes to the fate of the lowest mass stars that are actually stars. In other words, they do have fusion reactions. Those fusion reactions at that low mass end go extremely slowly. They're very cool stars. They're fusing. Their gravity, of course, is modest because they're low mass. And their fusion rate is therefore also slow. And so they're miserly with their fuel. They can eke out their fuel for a long period of time. And so but eventually it will be exhausted. There will be insufficient temperature and pressure to cause energy release by making deuterium, say. And at that point, the star will slowly cool and fade as an ember. And that will take forever, essentially. So there's this very long, slow phase of a star fading to black as the energy is lost, as the star slowly cools, essentially, literally like an ember, eventually cooling to 0 temperature. And at that point, it becomes invisible.
So kind of a related question from Making Math Easy is a pulsar called ARSCO has a diameter of 12,000 kilometers, which is similar to white dwarfs. So why do we consider ARSCO as a pulsar instead of a white dwarf?
Right. That's a good question. Well, the size of stars depends on their structure, their internal structure. A pulsar is a neutron star, so it's made of pure neutron material, and you can work out what the density of that is and the size of that is. And those stars, of course, are really small. I mean, neutron stars are a few tens of kilometers in diameter, and that's it. White dwarfs are substantially larger because they're substantially lower density. They're a degenerate material where the pressure that stops them from collapsing further is electron degeneracy pressure, which means no 2 electrons by quantum theory like to have the same set of quantum properties, and that creates implicitly a physics type pressure to keep the star puffed up. So generally, white dwarfs are substantially larger, physically larger than neutron stars or pulsars. And we can usually measure that difference. They also differ in their rotation rate. White dwarfs will rotate in the way the angular momentum law would dictate, given that they collapse from a larger state. And neutron stars similarly, but they've collapsed to maybe 1,000 times smaller state, and their spin rate will be correspondingly higher.
Thank you very much. The next question is from Carla, who would like to know what are some of the challenges and what's necessary to become an astronomer?
Astronomers tend to start their lives by studying physics because the sort of basis of physics, of astronomy and astrophysics is physics itself. It's the laws of physics applied out into the universe. So majority of astronomers, not all, but maybe 2/3 to 3/4, especially in the United States and Europe, had their first degrees in physics. And they would have had some astronomy as part of that degree. Now, there are also programs, and we have one here in Arizona, University of Washington has a big one, Texas has a big one, There are programs where astronomy is a major, so you can study astronomy as an undergraduate. Now you're still studying physics and math, so the triumvirate of physics, math, and astronomy is part of any training of an astronomer. The relative amounts of physics and astronomy depend on whether you're in a physics majors type program or an astronomy majors type program. And you can get into astronomy from a math major, and much less frequently you can get into astronomy from a biology major, if you want to do astrobiology, or from engineering majors. It's much less common because in the end you will need that base coat of paint of physics to get through the, say, graduate work in astronomy for sure, and even the advanced undergraduate work. So that's the core training of most astronomers. Now, amateur astronomers are working at a very high level in their field, and they may or may not have that formal training. Many of the amateur astronomers I know are retired doctors and engineers and lawyers and so on. They're professionals, but they don't have a lot of scientific training. They've just learned a lot of astronomy. And I guess that's the main distinction I would make, that if you want to be a career astronomer and get paid to be an astronomer, you really do need that scientific training. Picking up a lot of information about astronomy by observing a lot and having your own telescope is really nice and really important, but in and of itself, it will not probably land you a job as an astronomer. It's a qualification-based career.
All right, the next question is from Frag, the Desert Vagabond, who's on with us live, who would like to know, what do you think about the possibility of a fifth force of nature?
Well, it's always possible because we don't have a proper theory of unification of the four forces we have. So the four forces we have, each in their own domains, we understand fairly well. The electromagnetic force, of course, explaining how radiation behaves. The weak force in the nucleus of the atom, and we understand radioactivity, which is caused by that operation of that weak force, so we understand that pretty well. The strong force in the nucleus, which is what keeps nuclei intact and means that we don't see free quarks in the lab, that's also fairly well known. And then gravity, where we've had, of course, theories starting with Newton and then now with Einstein for a century. So these are pretty mature theories of four forces. But the super force, or the underlying theory that explains why these four forces have such different behaviors, properties, strengths, ranges, they're very different in every aspect. That's eluding us. And it's not necessarily a fifth force, but it's an opportunity for a more overarching theory that could have quite a different flavor from any of the four individual forces. And in that sense, it will act like a fifth force. Now, is there just a different force of nature just purely parallel to the four that we know about with similar strength to one or other of them? Probably not. We would have seen evidence of that in our observations, either in the physics lab or out in the universe, and we haven't seen that evidence.
Thank you very much, Chris. The next question is from Crystal, who would like to know, how do we know the mass of exoplanets?
We know the mass of exoplanets very directly when they're detected by the Doppler method, because the Doppler method is essentially a measurement of how much a star that you observe, because the observation are of the parent star, not the planet, is being tugged backwards and forwards by the planet that orbits it. And that tug, it's called a reflex motion in physics. That tug, the amount of the frequency shift, blue shift and then red shift, as the planet and star move towards and away from us in their orbit, it gives a very direct measure of the mass of the planet relative to the star. And we can say what the mass of the star is because we've got spectra of it. We probably have its distance and its temperature. We have a lot of physical information, so we can estimate the star's mass. And then the detection of the planet data gives us the mass of the planet. So that's how we know the masses of hundreds of exoplanets. Now, the exoplanets that are detected by the transit or the eclipse method that was used by the Kepler satellite, that's not a method that gives us mass. That method just looks for how much the light of the star is dimmed as the planet crosses in front of it, which really only tells you how big the planet is. You would have to then assume something about what the planet is made of to convert its size, or equivalently volume, into a density by knowing its mass divided by volume. and that would tell you what the planet is made of. So we don't measure mass by Kepler observations or by that technique, but there are hundreds now of exoplanets which have had the mass measured by the Doppler method and their size measured by Kepler. And for them, we know their density, the mean density. We know what type of planet it is, a terrestrial planet or a Uranus, Neptune type planet or a giant Jupiter. We can say pretty reliably what the planet is. And so hundreds of exoplanets have their mass measured, and that's good enough to give us an idea of the population.
All right, the next question is from Terrace, who would like to know if it's possible that supermassive black holes could exist outside of a galaxy instead of just at the center.
Yes, it is, because supermassive black holes generally will sit at the dynamical center of the galaxy, like our galaxy has a black hole 4 million times the mass of the sun, and they'll be very much tethered and rooted to the center of this big mass distribution of stars. However, when galaxies combine, and they each have massive black holes in their nuclei, those black holes combine. And so you have galaxies merging, and you have their supermassive black holes merging. And depending on the trajectory in a merger, it is quite possible for one black hole to eject by a sort of version of a slingshot mechanism that we use to direct spacecraft around the solar system, to eject the other black hole from the system entirely. And so there's a mechanism that's known, and you can simulate it in a computer, whereby in merging galaxies, one of the supermassive black holes, or both, actually, that's less likely, but could be ejected completely from the galaxies and therefore be floating free through space, these huge black holes, which is a bizarre thought. Has this happened? We don't have evidence that it's happened. We've never found a massive, supermassive black hole in intergalactic space, but our calculations and simulations of the phenomena suggest that it does happen, not often, but occasionally. And so those kind of free-floating black holes should exist, and we should keep looking for them.
Thank you, Chris. The next question is from Gan Shyam, who's on with us live, who would like to know, what is the theory of relativity, and can you explain it in sort of a simple way for him to understand?
If you mean general relativity, which I think is the harder of Einstein's theories to understand, the best way to understand it is the one-sentence definition, which is that the curvature of space-time is dictated or governed by the energy density of mass. And that's a simple way of putting it, that rather than living in smooth, three-dimensional, linear, Euclidean space, we live in space that could be highly curved. And the amount of that curvature, which is what Einstein's general theory of relativity equations are designed to calculate, the nature of that curvature is determined by the mass energy concentration in any region of space, or if it's the universe as a whole, by the global mass energy density. So that's the simplest way of expressing general relativity, and observations show that it's a good description of nature.
All right. Thank you very much, Chris. The next question that we have is kind of related series of questions. Who names things in space? How did the stars get their names? And how do exoplanets get their names?
So naming in astronomy is actually quite complicated, because there's thousands, hundreds of thousands, millions of objects in the night sky, as seen through deep observations with telescopes. And, naming all those can get difficult and tedious and complicated. For the bright stuff, it's fairly easy. The visible stars in the naked sky, the ones that have names, not all of them have names, were named hundreds of years ago, thousands of years ago for the most part, in antiquity. And so the brightest stars in the sky were named literally thousands of years ago. Most of them, although they were named by ancient civilizations like the Sumerians and the Babylonians and the Egyptians, very many of the bright star names come to us from Arab astronomers from around the time of the Islamic Empire in the 7th century through to the 11th and 12th century. So And it's very easy to see which of these stars they are. Any star that has AL at the beginning, which is the in Arabic. So you have Aldebaran and Betelgeuse. So many of the bright stars in Orion, for instance, Alcor, and so on. Just go through a star list and you'll see many that are actually Arabic. And that's because the Arabs traveled using stars as their guides in the night sky, especially in the summer when it's too hot to travel during the day. And so those bright stars bear names that go back to that distance. Now, not all the 6,000 visible night sky stars have Arabic names. Some come from other cultures, from Egyptian culture and Roman culture. And a lot of the planet names, and especially the moon names, they're almost all rooted in Roman and Greek mythology. So that's where a lot of planet and moon names come from. Now, for the fainter objects, like the faint stars too faint to see with the naked eye, or the millions of galaxies you can see with a modest-sized telescope, they simply don't have simple names. So Andromeda is M31. It's named as a Messier object, and it's named for the constellation that it resides in as the brightest galaxy. But once you get to fainter objects that are more anonymous, they just don't have names anymore. They just have designations that are essentially a compact version of their sky position. They're in the coordinate system, in the equatorial coordinate system that astronomers use of right ascension and declination. So the average astronomical object, deep sky object, has rather boring naming because it's essentially a position designator designed to help people know how to find it with a telescope. Occasionally, a deep sky object gets a name. There's an object called Hoag's object. There are, there are galaxies that Helton Arp, an astronomer at the Carnegie Institute in the mid-last century, named hundreds of peculiar galaxies in his catalog, the ARP Atlas. So there are definitely galaxies and even some quasars and active galaxies that are named after people or from their mode of discovery. But I would say 99.999% of all the objects that astronomers study with their big telescopes are not named after people at all.
All right, and we are at the end of our time available. So the last question, there are several questions about this, so I'll kind of roll them all into one, is about white holes. Can you talk about what they are, and whether they exist, and whether they could possibly exist? And then when you're done, we can wrap up.
Mm-hmm. Sure. I mean, white holes are intriguing to people. They're as intriguing in a sense as black holes. Kip Thorne, a very eminent gravitational theorist at Caltech, has written a popular book. I can't remember the name of the book off the top of my head, but if you look him up as an author, Kip Thorne, Thorne, his popular science book on black holes and white holes and wormholes is very well done. And he's an expert in his field, so he probably frames these issues as well as anyone I know or have read. So the basic summary of white holes is there's no evidence that they exist. It's not even obvious how astronomers would know how to detect something that they knew was a black hole, a white hole, as opposed to any other source of energy and radiation localized in the sky, because these are obviously physically small objects. A white hole, if it exists, is just as small as a black hole. A white hole could, in principle, result from a tunneling in space-time between two different regions of the universe, where energy and matter was flowing in one end at the black end and coming out of the other end, the white end. That's very simplistic, but that's one of the modes of a white hole. But while that is possible, while space-time could do that, in our universe, it seems that space-time is very simple. There's not a lot of convolution. There are not a lot of just remote regions of the universe that appear to be connected to each other by curvature. So the universe we live in is a little mundane and boring compared to the universe that would give you white holes to study. Nonetheless, people retain interest in them, because if they were found as portals between very different places of the universe, that would be extremely exciting. So I would say they're esoterica of astronomy. They're speculative and unconfirmed, and we didn't even really know how we would find one. but they're going to stay on the margins of the subject as of interest to astronomers as well as people who care about astronomy. So thanks for your questions, varied and interesting as always, and thanks to Matthew and Alexander for facilitating this session, and we'll be back with you in a week or two.